In this video, we're going to look at an alternative way of integrating an inverse. So, for example, this is an inverse. Um, this here is another example of an inverse. This here is another example of an inverse. Natural log is another example of an inverse. So, natural log is this. It's an inverse of e to the power of x. So when integrating an inverse, our old method would be to do this. Our old method of integrating would be to do this. Set it to 1 here. That's our trick. So now in this video, I'm just going to zoom through how we would normally do it, and then I would introduce a new way, an alternative way of doing it. Learn the alternative way as well, because it will give you a better understanding of what's going on, and it will give you more flexibility in what you're able to integrate. Okay, so our normal way of doing this would be to do this. So set it to be set v prime to be 1, set this to be our u, and then we would blindly follow this. So if u equals this, then u prime would equal this. If v prime equals this, integrate it, that would then give you this, and then we would then just blindly follow this. So it's saying get u times v, it's saying get u times v, so that would be x inverse cos of x, and then you've got your minus the integral of, it's saying u prime times v, so that would be minus x over root 1 minus x squared dx here, and then we would then need to integrate this. Then this whole thing here would then become this, would then become this, but we still need to integrate this. So rewrite this bit here as a 2, but then cancel it out with a half out here. So now this here is the exact derivative of this. So integrate this, it will then give you this. Okay, it will then give you this. We've done this before, so you by now you should understand this. So integrate this, it will then give you this. So overall, our answer would be this. So this is our old way of doing it. So our old way of doing of integrating an inverse would be for us to do this. Imagine it as being a 1, and then this here to be our inverse here, and then we would follow the process, and then it would take you to here. This is our old way of doing it. Now the alternative way would be to rewrite everything in terms of y. So for example, we are trying to integrate this. So let's just say y equals this thing here. From here we would cos equally to both sides. That would then give us this, and then now from here we are able to jump to here. And the reason why we're able to jump to here is because of this. So we would differentiate this as normal. That would then give us this, and then it would be dy, and then on this side here it would be 1, and then dx here. From our section on differentials, we are able to jump from here to here, and this is from a section on differentials. And the reason why you're able to jump from here to here is because of this. Hang on. Is because of this. So let's just look at this, for example. If you were to differentiate this, you would from here you would just say dy by dx equals 3, and then from our section on differentials, we are able to treat this as one entity. So we can actually times both sides by dx here. So from here we are able to do to just jump to this 3 dx. So that's this. From here we are able to jump from here to here. Okay, our section on differentials allows us to do this, jump from here to here. So another example is this. So from here we when we differentiate this, normally we would just say, when we use implicit differentiation, we would differentiate it as 3 3, and then, sorry, when we use implicit differentiation, our normal routine would be to differentiate this as normal, which would be 3, and because y is a function of x, we would have dy by dx. And then we would differentiate this, that would then give us y. But then we're able to, from our section on differentials, we are able to move this across here. So that would be, well, from here, differentiate it normally, that would then give you this. But then from our section on differentials, we are able to jump from here to here. So so if you have 3y equals 5x, you're able to do this. Differentiate this as normal, which would be 3, and then dy here on this side. Differentiate this, and then this will be dx. So from our section on differentials, we are able to do this. So if you look at this, hang on. If you look at this here, we would so normally using implicit differentiation, we would jump from here to here. So this is something that you're able to accept. From our section on differentials, when given this here, we can do this. Differentiate this as normal, which would be 6y, and then we can stick the dy in here. This side here, differentiate as normal, which would be 5, and then stick the dx in here. This thing here is exactly you can accept this from implicit differentiation. From our section on differentials, we can jump to we are able to jump from here to here. So when given this, when given this here, implicit differentiation allows you to jump from here to here. So you're able to accept this. Now, from our section on differentials, we would, when given this, we would differentiate this as normal, which would be minus sine y. What's this x doing here? That should be a y. Hang on. That should be a y. So from our section on differentials, we would start from here. We would start from here. So differentiate as normal. So that would be minus sine y, and then dy. And then on this side, it would be 1. Differentiate as normal. That would be 1, and then stick the dx in here. So this bit here is, now let me just change this. This bit here is this. So this bit here is this thing here. So implicit differentiation, you're fine with it being able to jump from here to here. Now from our section on differentials, we are able to jump from here to here. That is perfectly legal. Okay, so hang on. So we were trying to integrate this. So from here, we are trying to integrate this. So let y equals this thing here. So if y equals this thing here, then from here we are able to jump to here. And then in the next video, I will show you how we will proceed from here. Okay.